Happy morning, dear friends. Here's yours, Dr. Ajanta. Welcome to Demystify with Ajay. Dear friends, today in this episode, we are going to discuss on image recognition. In the ever-evolving landscape of artificial intelligence, groundbreaking models and techniques are constantly pushing the boundaries of what possible in computer vision, 3D vision, and multimodal understanding. Today we will be diving into some of the latest research papers that focuses on enhancing efficiency, adaptability and accuracy in this dynamic field. Let's explore the advancements that are shaping the future of AI. And of course, dear friends, you can find the full paper link in the description. If you reference this paper in your research, make sure to cite it. Dear friends, of course, the first exact paper what we are going to discuss is Hardwiring ViT Patch Selectivity into CNNs using patch mixing. Vision transformers. Dear friends, actually vision transformers, which is shortly specified as VITs, has brought a revolutionary shift to computer vision, often outperforming CNNs due to their unique ability to model non-local dependencies and use a self-attention mechanism. One of the most fascinating aspects of VITs is their ability to ignore irrelevant or out of context information while focusing on in-context features, the concept known as page selections. This property is particularly useful when dealing with occlusion in images, so where irrelevant part of the image can be filtered out early in the network. Difference in this paper, the authors explore whether convolutional neural networks, which traditionally rely on local featuring processing, can achieve similar patch selection. The solution they propose is called the patch mixing. So a data augmentation technique that involves mixing patches from different images. So the idea is to insert patches from another image into the current training image and interpolate the class labels accordingly. This data augmentation method forces the CNN to learn to focus on the in-context patches, simulating the patch selectivity behavior of VITs. Dear friends, by hardwiring this inductive bias into CNNs, they hope to enhance CNN's ability to handle occlusion and improve generalization. The study's results show that patch mixing is an effective strategy to enhance CNN's performance and bring them closer to ViT's patch level selective processing. Okay, in the next paper, it is all about MSViT. That is the exact name specifies. So, dynamic mixed scale tokenization for vision transformer. Dear friends, a key limitation of vision transformers is that they process images by splitting them into uniform patches, regardless of the content of those pages. So this approach doesn't differentiate between dense area and uniform background area. Dense area, that is actually a highly informative part, or could later be just specify. And if it is a uniform background area, so which carry less semantic values. Okay, so this uniformity leads to inefficiency in computation and limits the model's ability to focus its resources on important image regions. Dear friends, the authors of this paper proposes MSViT, that is Mixed Scale Vision Transformer, which introduces a dynamic mixed scale tokenization scheme to address this issue. So the core idea is to apply a conditional gating mechanism that adapts the size of the tokens based on the content of the image. And for instance, region with a complex, that is high detailed information are processed with smaller token to capture fine, greater or grained features, and while simpler region, and then is like a uniform background, are processed with larger tokens to save computation. This gating module is lightweight, so flexible, that is it can work with any ViT backbone, that is easy to train with minimal overhead, by incorporating a batch shaping laws to enhance the gate's performance. This MSViT is able to focus on the most important parts of the image while avoiding computational waste. When validating on classification and segmentation tasks, this MSViT demonstrated an improved accuracy complexity trade-off, offering a more efficient and scalable approach to vision transformers. Next paper, it is GPT-4 ROI, instruction tuning large language model on region of interest. Difference: while large language model has demonstrated remarkable multimodal abilities through instruction tuning on image text paths, they traditionally align at the image level, lacking region level alignment. So this limitation restricts their ability to handle fine-grained details within images, such as understanding specific area or object in the scene. Difference: in this paper, the author proposed GPT-4 ROI. So GPT-4 ROI, that is a region level vision language model that overcomes these limitations by instructions tuning, that is LLM on region of interest. So instead of focusing on the image as a whole, GPT-4 ROI processes bounding boxes as spatial instructions, so which represents specific regions within the image. These regions are then paired with language embedding to create a more detailed understanding of the visual context. The new approach enables enhanced interactivity and controllability. So users can interact with the model by providing both language-based and spatial instructions, so allowing for more flexible questions, adjustments based on the detail level of the query. And dear friends, of course, this GPT-4 ROI also supports multi-region reasoning, where the model can handle multiple regions at once, providing more descriptions and complex reasoning about various objects in the image. And furthermore, yes, the system can integrate with any object detector to provide detailed attributes such as color, shades, material, action, and even relationship between objects. So this region level alignment opens up new possibilities for tasks like detailed image captionings and fine-grained visual reasoning. Okay, next paper, it is Patch and Pack. So NaViT, a vision transformer for any aspect ratio and resolution. Difference: in the world of computer vision, images are often resized to a fixed ratio before processing, so which can lead to loss of crucial detail, especially in non-standard image sizes. Traditional models, including CNNs, are designed with fixed size inputs in mind, so which limits their ability to handle images of varying aspect ratios or resolution. The authors propose a solution in the form of NaViT, that is Native Resolution Vision Transformer. So a vision transformer model capable of processing image with arbitrary resolutions and aspect ratio. Difference: this NaViT uses a novel approach called sequence packing during training, so which allows the model to process image in their native resolutions without needing to resize them to a fixed size. So this flexibility leads to more accurate and efficient processing of image with varied formats. And yes, dear friends, this NaViT says flexibility doesn't stop at image input. It also offers improved training efficiency, particularly in large-scale image text pre-training. The model can be transferred to a variety of standard computer vision tasks such as image classification, video classification, object detection, and semantic segmentation. So where it has shown improved performance on robust and fairness benchmarking. And at inference time, this NaViT's ability to handle diverse image size enables it to efficiently balance the cost performance trade-off based on the input resolution. So this marks a significant departure of the traditional CNN-based pipeline. Also suggesting that ViTs like NaViT, that is Native Resolution Vision Transformer, could lead to a more robust and scalable approach to the computer vision task. Okay, next the paper, it is all about 3D LLM. So injecting the 3D world into large language model. Difference while large language models and vision language model has shown impressive results in tasks like common sense, reasoning and multimodal understanding, they fall short when it comes to tasks grounded in the 3D physical world. So these models lack awareness of crucial concepts like spatial relationship, awkwardness and physics. To address this gap, the authors proposes the introduction of 3D LLMs, a novel class of model that integrate 3D point clouds with the large language model's capabilities. So enabling the model to handle tasks requiring spatial reasoning and interact with the 3D model. Different 3D LLMs leverage a combination of 3D feature extraction from rendered multi-view images and 2D VLMs as background and to process these 3D features. The model employs a 3D localization mechanism allowing it to better capture spatial information. So the author demonstrates the power of 3D LLMs through extensive experiments, including tasks like 3D captioning, question answering, and 3D assisted dialogue. On benchmarking like ScanQA, 3D LLMs significantly outperform existing model with improvements such as 9% increases in Blue 1 score. So of course you are able to view this, I think so. Okay, yes, this result highlights the potential of 3D LLMs to tackle a wider range of tasks than traditional LLMs and VLMs, so pushing the boundaries of spatial reasoning and multimodal interaction. Okay, next the exact paper, it is on NeRF-Det. So learning geometry-aware volumetric representation of multi-view 3D object detection. Difference indoor 3D object detection has long been a challenging task, primarily due to difficulties in modeling complex geometries. Existing methods often struggle to capture the intricate spatial relationship between objects. To solve this problem, the author proposes NeRF-Det as method that combines the power of neural radiant fields with traditional 3D detection technique to generate geometry-aware volumetric representation. Difference this NeRF-Det stands out because it introduces a joint training design where the detection and NeRF branches share an MLP that enables the seamless integrating of NeRF for 3D geometric estimation and object detection. Dear friends, the author incorporated geometry priors to help NeRF optimization. By adopting this approach, NeRF-Det significantly improves performance on 3D detection tasks, outperforming existing state-of-art methods by 3.9 MAP, the ScanNet benchmark, and 3.1 MAP and ArcGIS scenes. So kindly have a note on towards this. And yes, dear friends, the model's ability to generalize exactly. So it is exactly generalizing well to unseen scenes without pure scene optimization also. So making it highly adaptability for tasks like view synthesization and depth estimation, marking a major step forward in indoor 3D detection. And that brings us to the end of this episode. Yes. And yeah, that brings us to the end of this episode. Yeah, we have discussed the research papers in computer vision and multimodal artificial intelligence, from dynamic tokenization in vision transformer to 3D spatial awareness in large language model. These papers represent significant strides forward in the field. So if you found these advancements and excited as I did, yeah, make sure to like, share and subscribe for more insightful updates on the world of artificial intelligence. Dear friends, drop your thoughts and questions in the comments. I would love to hear your perspective, and if you are come across any papers related to this topic discussed, feel free to share them with us. So thanks for watching, and I will see you in the next episode. Happy learning, dear friends.